Next, we have Dr. Denis Schiozer from the University of Campinas, all the way from Brazil as well.
Good morning. First of all, thank you, Energy Simulation, for organizing this event. It's a pleasure to be here again in person, and thank you very much for the attendance. My name is Denis Schiozer. I'm from the University of Campinas in Brazil. The focus of our research group is the model-based and data-driven reservoir management for future applications in digital fields. We are doing research in reservoir simulation for many years, and we are using this reservoir simulation for life cycle objectives, for life cycle forecasts and decisions. And the industry in Brazil challenged us 2 years ago and to how we could use these models in digital fields, in real-time decisions, and so on. So we start changing a little bit the focus of some of the projects there to develop methodologies to improve the quality of the models for short-term decisions, not only for life cycle decisions. So today I'm going to present a little bit of this focus. Our research lines are concentrating in this methodology that I'm presenting here, which is the model-based closed-loop field development and management. We are doing research in several aspects of this figure here, but basically we divide this in 4 colors. We have many people working on how to build these high-fidelity models, the ones, for example, the ones that Leonardo was showing previously. When we do that, the simulation models take a long time to run, especially for the pre-salt in Brazil, which are very complex and giant fields. So it takes many hours to run. So part of our research group is dedicated to how we could build this fit-for-purpose models that tries to bring the best quality of the models, but in a reasonable simulation time. And we also include all the uncertainties that we have. That's why we have multiple boxes in the green part here to incorporate all the uncertainties for the life cycle forecast and life cycle decisions. Once we have this, we also doing some research in how we can use multi-fidelity models to apply in different parts of the decision-making process that we are applying in this reservoir management process. But once we have these models, we have to honor the best data. So we go into this red part here, which is the data simulation or history matching part. We are doing a lot of research, especially in Brazil. They have a lot of seismic 4D, and we are trying to incorporate all this seismic 4D data to improve the quality of the models, even changing directly the simulation models or changing the geological models and doing this big loop. But when we do that, we also have a big time to run, so we have to speed up the process and simplify the models and have models that run in a reasonable time. But once we have the models that calibrate, that honors the past, we go into this blue part here, which is like cycle production optimization, where we apply robust optimization process to improve the quality of forecasts, improve the quality of decisions we take for the reservoir, especially for the pre-salt in Brazil. We include some operational noise, not to have biased results. Similar to the noise we have in real life, delays and other things that we can apply that. Then we apply the production strategy into the field, and we capture the production data and seismic 4D data, and we start all over again. And we apply these cycles many times until the end of the reservoir's life. So the typical size of the closed loop is 6 months. It can be less or more depending on the quality of the reservoir simulation models. And we apply this loop several times. But what we are trying to do in this research, and I'm showing today, is to apply this black part in the top, where we try to decrease the size of the loops and shorten the time of decisions. And our objective is to shorten that until we go to real-time decisions. So we the focus of the presentation today will be how to integrate these life cycle decisions into this black part, where we have many sub-loops, and so we go into this black part several times to improve the quality of real-time decisions. So this is the same picture with, it's a little bit complex to explain, but it's just a zoom in the black parts. So we have the red part, the green part, and the blue part that are simplified. And the idea is to apply the same techniques we are applying from last years to optimize production in this blue part. But this is not the real decision. This is just a set point for a short-term management that we are going to do in the black part. So in this short term, we are considering now several aspects, different aspects in order to improve the quality of the real-time decisions we apply. So we have these sensors, we have the short-term decisions, we can correct the decisions that we take for a lifetime, and we can concentrate in the decisions we're going to take in the next days or next months. So this black part, I'm going to show just a few examples today. We divide the variables in 3 groups in order to apply automatic procedure in order to optimize this, because it takes a long time to run all the simulation models and everything takes an hour. So we have to be everything automatic. So we divide the variables in 3 groups. The group 1 is our development phase of the fields. That we call design variables. The group 2 is the management variables, where we can optimize the controls variables and the valves and ICVs and the control of the wells. And group 3 is the revitalization variables that for the pre-salt are very important, because in the pre-salt we have limitations in gas production, the platforms. So the companies are applying the production strategy in waves. So we can have second and third waves where we have new wells in order to use this full capacity of the gas production in the platforms. So the idea here is and then to divide this group 2 of the control variables in 3 lines. One is the group 2L, which is the life cycle decisions, which are optimized robustly using our current simulation models. There are set points for the group 2C, which is the variables that we can control in the cycles. So we don't optimize the variables that are going to change in a few years, on a few months. We concentrate in the variables that we're going to apply in the next loop of the closed loop. And then we are going to apply this to the short term and real time. If we are able to do that efficiently and in a reasonable time, we can then go to the digital fields and try to apply these optimization techniques into the real-time decisions we have in the fields. So we also have this operational noise that for short term are very important, because if you have problems in wells, we have to know what to do with all the other wells and how we manage all these variables that we have in the fields. And we also, I'm going to apply this, we're not doing that yet, but we're going to apply this to group 3, because we have to optimize these second and third waves that we're going to have for the pre-salt fields. So the idea here is to optimize everything as we are doing, but now concentrating in the variables that we can apply immediately in the fields. So the idea is to do the same thing in the blue part here as we show in the blue arrows here, group 1, group 2L, and group 3. And then we have sub-loops where we optimize the variables inside the loops. As we have less variables to optimize, we can have simple optimization methods and better management rules. And then we can adapt what the general plan, the life cycle plan, to real-time decisions. And every time you had to change the models, we go into this red part, which is the data assimilation process, that we are going to change the models and redo everything for the next cycle. So we try to improve this, to apply this into short-term decisions, but it was not so easy as we thought. We had several problems to apply our simulation models for short term, and we have to do a lot of modifications in the models. I'm showing some examples here why we have problems to apply that. So The first thing is that normally the simulation models that we apply for life cycle do not work very well for short-term forecasts. So we had to improve the quality of the models for short-term forecasts, especially in the new process for data simulation and history matching, because for short-term, the productivity of the wells are very important for real-time decisions. And normally we don't do that very well, very accurately when we think about life cycle decisions. I'm going to show some examples here. The second thing is that we have to improve the estimation of the boundary conditions we're going to use for the future, which is normally different from the boundary conditions we use in the history matching process. And the first important part is to apply what we did in the previous chair period, which is the integration of production facilities, because that's the best way to get the better boundary conditions for that. And also we had to call a different way of boundary condition. We call it human intervention free, but because of course, if a human goes there and change the well, close the well, we cannot predict that using a model, right? And we have to have boundary conditions that we could automate in the process. Like we have the restrictions, we have management rules and so on. This we can apply, but we cannot apply a rule that a human goes there and close a well. So we had to change a little bit this process in order to have different types of boundary conditions for the future in order to predict that very well in the simulation models. Another thing that we are trying, and we are getting the first results nowadays, is to use data-driven production and pressure forecasts in the cooperation of other professors from the University of Campinas, and use this data-driven process as to help us in the boundary conditions for the simulation models. So we call that hybrid approaches, where we use data-driven correcting models, and we use the probabilistic scenarios that we have for a life cycle to use as boundary conditions for data-driven. So we are using both models together in order to improve the quality of the short-term forecast and decisions. So this is a typical example why the simulation models are not working very well for short-term decisions. I'm showing here a picture of a real case in Brazil for a field that we have. And in gray, we have the prior data, and in orange, we have the posterior data after history matching. So if you see in the past, all the models are going very well. They honor all the simulation, all the real data. But if you go into the validation period, as we go there, the reservoir simulation models have an uncertainty in the production and productivity that can give us a very wrong rates for the short term. In a long time effect, the material balance of the reservoir will accommodate these errors, and the error will not be so high. But for short term, as you can see, we have more than 100% errors in rates. And if you want to control the ICVs and the wells in order to improve the quality of the reservoir, these errors are very important. So the first thing to do, we have to correct this type of errors that we have in normally simulation models. We can do the same in probabilistic models, as we can see here. In the left, we have the figures of another real case in Brazil. We have one well, and the pests, which is below 2,000 and 1,300 days, honors the pest perfectly, and the history matching procedure is working perfectly. But if you go into validation period where we use the history data, but we use it in the prediction mode, in the forecast mode, the errors are very big and the models don't behave very well. We have to correct this. In this case, we have to correct this for the productivity of the wells. These are heavy oil fields where we have a very different productivity if we produce oil or water or different water cuts and so on. And we have to predict this very accurately in order to have an accurate forecast for the short term. After we do this, then we have a much better result for short term, and we have a better result. We can manage the wells much better. Another problems that we had in real problems that don't occur normally in our simplified simulation models is that when we integrate with production facilities, we have errors also in the production facilities modeling. And I'm showing just one example here. In the left, we have a model that we have a perfect history matching in the past, as we can see in the history data there. But when we go into the forecast modes, the errors that we have in the models in the production facilities cause a very big errors in the futures. As you can see, the difference between the red line and the green and the blue lines there. The red line is the data, real data, and the others are simulation models. And why this happens? Because the production facilities also have errors. And then we start applying like a similar history matching process to calibrate the production facilities, the pressure drop in the production facilities and the pumps and so on. We have to calibrate this to real data. When we do that, we have the results we have in the right side there, where the results are much better. The blue lines, which are the models that we are going to use for forecasting decisions, are much closer to the red line. So we have to apply history matching not only in the simulation, reservoir simulation models, but also in the production facilities modeling. And when we put those together, we have much better results for that. Once we have these better results, again, we can use these models for short-term forecasting decisions. Another common problems that we have, these are complex graphs as well, but this is an example of a real example of a project we have with Shell in Brazil. And for real fields like this one, we have a lot of operational problems, as we can see in the dots and red dots and blue dots we have in the left part, because wells are changing every time, the controls are changing every time, and we have to predict, we have to have a forecast mode, which is the right graph. For life cycle, it's okay. We can put an average and then we go and we predict the rates that we can give a good prediction. But for short term, this is very important. We have to understand very well how this behavior is happening and this oscillation is happening. Which type of oscillation is caused by what? Some of these oscillations are production problems. Some oscillations are because management rules, because the platform is in the top. So if you change one well, you change the others. And so in order to do that for short term, we have to understand, we have to integrate with production facilities, have a very good idea of the productivity of the wells, and then we have to integrate both systems in order to have a better forecast mode. This is not so easy as it looks like in the simplified models. In real life, we have all these oscillations, and we have to have a very clear understanding of the productivities to do that. So in order to improve also this productivity, we are integrating data-driven modes. And this is another example where the machine learning group are trying to apply data-driven to improve the quality of the short-term decisions. They used to say that their prediction is better, but we are showing an example here where we see the history and training. We use this history training to train data. When we go to the forecast mode in the history testing, as we can see the green there, the green line there, which is the data-driven data, is not good at all. Why? Because we didn't have this increasing water production in this particular case. So the data-driven cannot predict that, we cannot forecast that. So using pure data-driven approach is not good to predict the short-term decisions. So we have to integrate both together in hybrid procedures. Here are other examples and problems that can happen when we change from history to forecast modes. We can see that sometimes the data work better than the models, and sometimes the models work better than the data. So the idea, we are trying to put those together in order to avoid this type of problems that we are observing in some of these graphs here, where the green is the data-driven, the blue is the model-based, and the red one is the data, real data, right? So we have problems of all types and the problems are different from heavy oil, from the pre-salt, and we have to adapt all these methodologies in order to have automatic procedure to do that. So the steps we're taking into these digital fields are first to use reservoir simulation models for short-term decisions. The improvements we had to do so far was to a better transition between past and future for simulation models. The integration of production facilities is very important for short-term forecasts. And we have to have a better estimation of forecast conditions. And we also trying to teach all the students and postdocs there, emphasizing the difference between the control variables, the physical restrictions we have, the management operational problems, the maintenance problems, and so on, because these are very important for short term. For life cycle, these are not so important, but for short term, it's very important to understand all this difference in order to apply this to forecast the rates for the next days and next months. So the current steps we are taking is to improving the quality of the models, integrating with data-driven. And we are also observing how we can use multi-fidelity data, multi-fidelity models, in order to, maybe we can use different models for short-term and long-term, but integrate them together in multi-fidelity models. And for life cycle, we are also applying a probabilistic approach because the uncertainties play an important role. But for short term, these are many of these uncertainties don't matter for the next days. So we are also using different options to different models and different options to forecast mode for different life cycle and short term. So what we thought would be easy, we had to change the whole closed loop process. We had to change the models. We have to use multi-fidelity models. We have different approaches for data simulation and history meshing process. To improve the quality of the short-term conditions, we have to modify, we had to create methodologies to do the history meshing for the production facilities. And we have to change our robust optimization process and the blue part, the life cycle, in order to incorporate all this difference that I have shown in the examples. And now we are able to improve the quality of the decisions for the loop. Once we finish the loop, we are going to short term, which is the loop we're saying is 6 months. So I improved the quality of the simulation model for the next 6 months or 1 year. Now we're going to 1 month, and probably next year we will bring results for real-time data. When we do that, we are prepared to use these simulation models in digital fields. And our focus again is the application in the pre-salt fields, in the giant carbonate fields, and with permanent 4D intelligent wells in Brazil, especially considering that we have gas-driven optimization because of limitations in the platform. And we have 3 applications in the poster section. One is an application with polymer flooding with Equinor in Brazil. The other is an application of these approaches for decisions in infield drilling wells. In a field, we have a cooperation with Shell in Brazil. And the other one is a poster that shows the importance of the integration with production facilities in a project we have with Petrobras. So thank you very much for your attention. Thank you for your energy and the other sponsors. I would be glad to answer questions if you might have.
Thank you, Dennis. Any questions from the audience? Okay, there's one from Felipe Branco. Great presentation, Dennis. Congrats. My question is, what is your point of view of reservoir short-term predictions in order to ensure cash flow in an energy transition scenario? Do you believe the quality of data in the future could be integrated with life cycle to help decision process, or the results are still far away from this result? Quite a mouthful here, right?
Yeah, that's a good question, because one of the difficulties we are having is that when we optimize the production considering the life cycle objective functions, Many times the action for short term is different than when we optimize for short term. For example, if you want to optimize for oil production in short term, maybe this is not the best decision for life cycle. So it's an important question, and what we are doing is investigating this, doing research in different ways to do it, and try to apply this in different ways to see which is the best way to go. So if we use the objective functions of the life cycle, even for the optimization of the short term, it's okay. That would be the best thing, but the simulation models take hours to run, and we have many hours to go into this optimization, robust optimization process, and we don't have time, enough time for changing the decision in short term. So if you want to consider all the probabilistic, all the models, uncertainties and everything, normally it takes a few weeks to get any response. So we don't have time to do it. So what we are trying to do is a correlation between the objective functions of the life cycle and the objective functions for the short term. And then when we do all this automatic procedure for real time, we think we cannot wait weeks. So we have to do it in real time. So we have to incorporate all these procedure in the objective functions that we can deal with in short term. So this is still a challenge, because sometimes the decisions are different for short term and life cycle.
Okay, and one more question from online audience, Master Irani, which I have a probably similar question as well. So as you said, most commercial applications are not honoring the well PI. And also once you have the well with very restrictive ICD flow rate, it's more controlled by the ICD than the reservoir deliverability. So how do you differentiate between the ICDs in your AI model? Also, what if you have slight gas which makes ICD more resistance? Any thinking on that? I would piggyback on that myself, even potentially any kind of skin damage, workovers, mechanical problems that may kind of throw your AI off. So how would you handle that?
Yeah, that's one of the challenges that I was mentioning, because for life cycle, these problems are not so important, because we have the material balance of the reservoir will account for that in a long time, and we are working for average behavior. But for short term, for sure, all these aspects are very important. And one thing that we could observe is that our current simulation models are not very good for this type of problems, where we have these uncertainties in the productivities, and the productivities sometimes change, especially for heavy oils that we are testing in Brazil. They change a lot when we have water production, the increase in water cuts and so on. So we have to incorporate all this information, all this knowledge in this type of methodology. That's why it's taking more time to do it than we were expecting. Yeah.
Okay. Question from the audience here.
Hello. Yeah, thank you for your presentation. I'm Mark Zhong from SMG company, and my question is for your model. Actually, you mentioned for the data-driven model, do you using simulation outputs as an input to train your data-driven model? And the second question is, will you dealing with the hybrid model, combine data-driven model and the simulation model? How could you weight different results from different models? Thank you.
Okay, thank you. No, what we are doing so far, using only data to train the data-driven models. The professors from the machine learning group there are getting results, and sometimes the results are good, but sometimes they are not good because there are some changing behavior in the reservoir that they don't have data to guess that this is what would happen in the future. So the thing you are asking is very important, because that's what we are trying to improve right now. Is use not only data from the past to the data-driven model, but also the behavior of the models, considering all the uncertainties and limitations we have. We also are using this to boundary the behavior of the data-driven process. So this is improving the quality of the results. Of course, if the models are wrong, I will input something wrong in the data-driven, but that's why we are calling hybrid modes. We use the data from the past to predict the future, but we are also conditioning the future in the data-driven prediction into the boundary conditions we have from simulation models. And this is improving a lot the quality of the results.
Okay. Sorry.
My second question is, how can you hybrid the simulation model and data-driven model if these two models have significant difference?
That's a good question. We are not doing that yet, but we are planning to do that. And the idea is to, my thinking is that we are going to have to use multi-fidelity models, and we use different not the same models we use for life cycle and short term. We have to change information in between models and then integrate both together. And maybe you can talk later if you have other ideas, but that's my planning. Yeah.
Thank you.
Yeah, thank you for the good question. One last question from the audience, please.
Thank you for your presentation. Can I ask more details about your data-driven models? About your prediction model and the optimization model, can I ask what kinds of algorithm you utilize in your model?
Sorry, I didn't understand your question. Can you repeat?
Which machine learning algorithm you utilize in your data-driven prediction model and your data-driven optimization model?
Well, the model for machine learning, I'm not really, I'm not doing. The people from machine learning department that are doing. So I'm not, just using their results to improve the quality of my simulation models. So we are doing a cooperation together. They are testing different types of techniques to improve the quality of the data, and most of the techniques are working fine. But the problems that we are having are not the techniques. The problem is that the one that I showed here, when we have a sudden change in the behavior of the reservoir because of the restriction, because of the water that in the past was not in the well, and then we have an sudden increase in the water cut and this thing, they cannot predict that. So we cannot predict that. If that doesn't happen in the past, we cannot predict this in the future. That's why we are planning to use not only the data, but also the models. For example, the data predicts that we have 0 water production in the well, and I'm going to predict the next days, the data-driven model will produce 0 water production. But if the simulation models show that we are going to start having increase in water production, maybe we can use another hybrid approach to consider both options. And that's our planning. So far, we are using pure data-driven, which works fine in some cases and very badly in the other cases, and simulation models that are working fine for life cycle, but not so good for short term. So we are integrating both and trying to improve the quality.
Okay, and about your base reservoir simulation model, about the reservoir geology model, is heterogeneous or homogeneous? And how do you turn this reservoir model into the data for the data-driven model prediction?
Yeah, the models are very complex, very heterogeneous. The carbonate fields with 2 porosity, 2 double permeability models, and that's one of the problems that it takes hours to run these models. And if you want to use them for life cycle, okay, because I can wait a few weeks to have the response and have the changing decisions. But for real time, our current simulation models are not good because you are going to apply optimization, robust optimization procedure and automatic history matching procedure. Normally, it takes like 1 month, 2 months to get the answers and then to get the solutions, maybe weeks, but it can be months. And I cannot use this for short-term decisions, right? That's why we are trying to do models that are faster, but keep the same